We would like to continue our study of substitution for the indefinite integral, and also talk a little about the substitution formula for the definite integral. First of all, let's recall how substitution works. So it's based on the following formula. If you have the composite of two functions followed by the derivative of the inner function, then you can call the inner function u, and then formally du is g prime of x dx, and this ends up being the integral of f of u du. So we don't really find the antiderivative for our integrand. We just reduce the integration to finding another integral, which hopefully is going to be much simpler than the one we start up with. So let's do a few examples. So one interesting kind of example that we saw in the last lecture was something like this. Let's put as generic numbers as we can. So here we use the substitution u is equal to 7x plus 5, and of course du will be just 7 dx, and we will also need to solve for x, which is u minus 5 over 7. Of course, du being equal to 7 dx means that dx is equal to 1 over 7 times du. So now we can do our substitution. So we will have u minus 5 over 7. And then square root of 7x plus 5 is going to be square root of u. And then we're going to have 1/7 du. We multiply 1/7 times 1/7. That's 149, and we extract it outside. And we have u minus 5, square root of u. And now it's the usual story. We just need to multiply out to FOIL the integrand. So we will have u square root of u minus 5 square root of u du. We want to write everything in terms of powers. So 1 over 49 times u to the 3 halves. Why u to the 3 halves? U is u to the first. Square root of u is u to the 1/2. U to the 1 plus 1/2 is u to the 3 halves minus 5 u to the 1/2 du. And now we're ready to carry out our integration. 1 over 49 times, we have to go 1 degree up. So u to the 5 halves divided by 5 halves, which is the same thing as multiplying by 2/5. So u to the 5 over 2 times 2/5. And same thing for this one. So we have u to the 3 halves divided by 3 halves. That's the same thing as multiplying by 2/3. So this is going to be minus 10/3 u to the 3 halves plus c. I'm not sure that it makes a big difference if we multiply out. We can just do it. So 5 times 49 is 245. So this will be 2 over 245. U to the 5 halves, of course, that is going to be 7x plus 5 to the 5 halves minus 10, and this will be 147 7x plus 5 to the 3 halves plus c, and that's our final answer. You might want to stop the video and try to do the whole thing yourselves to make sure that you get comfortable with this type of computations. Now, let's turn to something different. Imagine that we have something like this. Cosecant of ln of x over x. How do we do cosecant square, actually? How do we do this integral? Well, first we're going to start with the substitution u is equal to ln of x. Then we know that du is going to be 1 over x dx. So here's your du. Okay, so this is going to be cosecant square of u du. And now we have to think, have we ever seen cosecant square as the derivative of something? Well, we know that the function cotangent has as derivative negative cosecant. So the antiderivative of just cosecant square, cotangent has derivative cosecant square. So the antiderivative of cosecant of negative cosecant square will be negative cotangent. So this will be negative cotangent of u plus c. And of course, we have to go back to our original variable. So this is negative cotangent of ln of x plus c. And that's all. Let's take a look at another one. So let's do one that will have a kind of interesting substitution. Let's try the integral of dx over 1 plus e to the negative 2x. Let's see how we do something like this. Okay, so there are different ways to think about this. And so one way to think about it is to try to simplify this as much as possible. So since you have a negative exponent, that will be 1 plus 1 over e to the 2x. And if you clear denominators, this will be dx over e to the 2x plus 1 over e to the 2x. And this will eventually be e to the 2x dx over e to the 2x plus 1. So now that we have written it this way, we can actually try u equals e to the 2x plus 1. And we will have that du is 2e to the 2x dx. And since we have e to the 2x dx, we want to isolate it to the 2x dx. And this will be 1/2 du. And now we're ready for our substitution. So let's carry the 1/2 in front. And this will be du over u. This will give us 1/2 ln of absolute value of u plus c. And this will end up being 1/2 ln of e to the 2x plus 1. I'm dropping the absolute values because the quantity e to the 2x plus 1 is always positive and there's no need to keep it there. Okay, now I said that this was one possibility. What is another possibility here? Let's see. Another possibility is to look at this. Actually, that's kind of more instructive. I will try to perform the substitution u is equal to e to the 2x, which seems rather provocative, given the fact that we have nothing like the derivative of this. But still, you will see that it is possible to carry out the substitution, suggesting that pretty much any substitution can be carried out. So du will be 2e to the 2x dx. And since we have nothing, I'm going to bring everything over to the other side. And here, the rule of thumb is that you never want to have on one side things that contain both variables. So this will be written right away as 1 over 2u du equals to dx. Okay, And now, since u is equal to e to the 2x, you can ask what is e to the negative 2x. And of course, e to the negative 2x is 1 over e to the 2x, which is 1 over u. So if we put everything together, this will give us 1 over 2u times 1 over 1 plus 1 over u du. And eventually you, of course, see that we get a very similar integral. Take the 1/2 outside, and this will be du over u plus u times 1 over u is u plus 1. And for this, either we can do it right away, or we can think of a second substitution. V is equal to u plus 1, dv is equal to du, and that will give us 1/2 dv over v, which is 1/2 ln of absolute value of v plus c. And this will need two steps backwards. So first of all, we go with respect to u. So this will become ln of absolute value of u plus 1 plus c. And finally, we replace u by e to the 2x plus 1. And as I said before, once you do this, you might as well drop the absolute values because they're not needed. Whether you drop them or not, it's certainly not a mistake. That's how we get our integral. Let's see one more. So how about cosine of square root of x over square root of x? Pause this video and try to see if you can get it. And we can try the substitution u is equal to square root of x. Du is equal to 1 over 2 square root of x dx. And then we can ask, what do we have here? And what we have is simply 1 over square root of x. So I'm keeping 1 over square root of x dx is equal to 2 du. I'm performing the substitution, and this will become cosine of u times 2 du. Take the 2 outside, and this will become 2 sine u plus c. And of course, we need to go back to our original variable, which gives us 2 sine of square root of x plus c. We would like now to look at the case of the definite integral. So what happens if we have a definite integral like this, and inside it has everything that we had in the case that we were starting a substitution for the indefinite integral, only now it's a definite integral. The first step is exactly the same. So you just do u is equal to g of x, du will be g prime of x dx. The next step needs a little bit of attention. So we actually do f of u du, so that doesn't change. But now the limits of integration go from g of a to g of b. So in other words, we substitute the limits a and b into the formula that we're using, or rather we apply the substitution to the limits of integration, and that gives us this new definite integral. The interesting thing is that once you get this definite integral, in the case of definite integration, you don't need to go back to your original variable. In other words, you can continue working with this integral thinking that you never even saw this before. You can ignore completely where it came from. That's the nice thing about definite integration and substitution. And let's do an example to understand how this is done. So let's say that you have something like the integral from 0 to 1 of 1 minus u to the third du. Oops, why do I start like that? I mean, it would have been perfectly fine, but let's say I have 1 minus x dx. So I said u is equal to 1 minus x, du is equal to minus dx, or dx is equal to -1 du. So now this is where we have to be careful. So 1 minus x is u, so this will become u cubed, right? And then dx is -1 du. And now this is where we have to be careful. We're supposed to take 0 and plug it in here. And then we're supposed to take 1 and also plug it in there. So if we take 0 and we plug it into our formula, what we're going to get is 1 minus 0, which is 1. So we put 1 here. And if we take 1 and we plug it into that formula, we're going to get 0. Okay, which seems at first very, very strange. Yes, but remember you have this -1, and you can always flip the endpoints of integration, the limits of integration, at the expense of a negative sign. So this is the same thing as u cubed du from 0 to 1. So that -1 that we had can serve as the way to flip this. And the antiderivative is going to be u to the 4th over 4 from 0 to 1. And notice now that, we just plug in, we get 1/4, and there's no need to ever go back and do anything with x again. So after our substitution has been executed, we forget where it came from, we forget the original integral, we just work with that, and that's all there is to it. There isn't any more. Okay, so that's all with substitution, both in the case of the indefinite integral and the definite integral. Thanks for watching.